Quantum computing is the future. The harnessed power of the subatomic world could soon upend the modern computing industry. Quantum computers are all over the news, and fundamental work on the theory that gave rise to them even won last year's Nobel Prize. But the one place you might not hear about them is inside a physics classroom. And if we have any hope of creating a technology-literate population and developing a workforce for this emerging field, that needs to change. What's a quantum computer? Unlike the computer sitting on your desk, which encodes words or numbers as collections of ones and zeros called bits, quantum computers rely on quantum bits or qubits, which are more, well, dicey, much to Einstein's chagrin. Unlike bits, qubits assign weights to their ones and zeros, more like how you would tailor loaded dice, which means there is a probability associated with measuring either number. They lack a definite value, instead embodying a bit of both states until you measure them. Quantum algorithms run on these qubits, and, theoretically, perform calculations by rolling these loaded dice, causing their probabilities to interfere and increasing their odds of finding the ideal solution. The ultimate hope is that math operations such as factoring gargantuan numbers, which now would take a computer billions of years to perform, would only take a few days on a quantum computer. This new way of computing could crack hard problems that are out of reach for classical processors, opening new frontiers everywhere from drug discovery to artificial intelligence. But rather than expose students to quantum phenomena, most physics curricula today are designed to start with the physics ABCs, riveting topics such as strings on pulleys and inclined planes. And while students certainly need to know the basics, there's room for Newton and Maxwell alongside Schrödinger's cat. There should be time spent connecting what they are learning to state-of-the-art technology. That matters because quantum computing is no longer a science experiment. Technology demonstrations from IBM, my employer, Google and other industry players prove that useful quantum computing is on the horizon. The supply of quantum workers, however, remains quite small. A 2021 McKinsey report predicts major talent shortages, with the number of open jobs outnumbering the number of qualified applicants by about 3 to 1, until at least the end of the decade without fixes. Thankfully, things are starting to change. Universities are exposing students sooner to once-feared quantum mechanics courses. Students are also learning through less traditional means, like YouTube channels or online courses, and seeking out open-source communities to begin their quantum journeys. And it's about time, as demand is skyrocketing for quantum-savvy scientists, software developers and even business majors to fill a pipeline of scientific talent. We can't keep waiting 6 or more years for every one of those students to receive a PhD, which is the norm in the field right now. Schools are finally responding to this need. Some universities are offering non-PhD programs in quantum computing, for example. In recent years, Wisconsin and the University of California, Los Angeles, have welcomed inaugural classes of quantum information master's degree students into intensive year-long programs. UCLA ended up bringing in a much larger cohort than the university anticipated, demonstrating student demand. The University of Pittsburgh has taken a different approach, launching a new undergraduate major combining physics and traditional computer science, answering the need for a 4-year program that prepares students for either employment or more education. In addition, Ohio recently became the first state to add quantum training to its K-12 science curricula. And finally, professors are starting to incorporate hands-on, application-focused lessons into their quantum curricula. Universities around the world are beginning to teach courses using Qiskit, Cirq, and other open-source quantum programming frameworks that let their students experiment on real quantum computers through the cloud. Some question this initiative. I've heard skeptics ask, is it a good idea to train a new generation of students in a technology that is not fully realized? Or what can really be gained by trying to teach quantum physics to students so young? These are reasonable questions, but consider, quantum is more than just a technology. It's a field of study that undergirds chemistry, biology, engineering, and more. Quantum education is valuable beyond just computing. And if quantum computing does pan out, which I think it will, then we'll be far better off if more people understand it. Quantum technology is the future, and quantum computing education is STEM education, as Charles Tahan, the director at the National Quantum Coordination Office, once told me. Not all of these students will end up directly in the quantum industry at the end, and that's all for the better. They might work in a related science or engineering field, such as fiber optics or cybersecurity, that would benefit from their knowledge of quantum, or in business where they can make better decisions based on their understanding of the technology. Quantum overturns our perception of reality. It draws people in and keeps them there, as the popularity of NASA and the moon landing did for astrophysics. We should lean into what captures students' attention and shape our programs and curricula to meet these desires. For those schools adapting to the emerging quantum era, the core message is simple: don't underestimate your students. Some might hear the word quantum and shudder, fearing it is beyond their comprehension. But I have met high school and middle school students who grasp the concepts with ease. How can we expect young students to pursue this subject when we gatekeep it behind years of pulleys and sliding blocks? Universities should start introducing quantum information much sooner in the curriculum, and K-12 schools should not shy away from introducing some basic quantum concepts at an early age. We should not underestimate students, but rather, we should trust them to tell us what they want to learn, for their benefit and for all of science. If we drag our feet even a little, we all stand to lose the immense benefits quantum could bring to our economy, technology, and future industries. Thanks for watching. Please like, share, and subscribe.